My name is Stu Wolf, and I'm currently a staff member at IDA, and was the DARPA program manager who created the Spintronics program in the mid to late 1990s. Before starting, if any of you have any questions, please use the app, and you can upload your questions, and we'll hopefully have some time at the end of the session to answer them. Now, the vision of Spintronics was to add electron spin to all of electronics, and hence the term Spintronics. Every electron has spin, but the spin was never really fully exploited in electronics until DARPA came along, until the DARPA program. That was strange, since it costs much less energy to flip a spin than it does to store a charge. And spin remembers, and charge usually forgets. Now, the story started in 1988 in France and Germany. Albert Fert and Peter Grunberg independently discovered that in thin film multilayers of alternating magnetic and non-magnetic layers, the resistance was very different. If the magnetic layers had their moments aligned, the resistance was very low. And if they were anti-aligned, like you would expect for a number of magnets, then the resistance was very high. They call this effect giant magnetoresistance, or GMR. And this was really the foundation of what was to become Spintronics. And in fact, they won the Nobel Prize in Physics for this discovery in 2007. In 1989, very soon after the discovery of the GMR, Stuart Parkin, who was at IBM at the time, developed a novel magnetic sensor called the spin valve. And this sensor was also based on GMR, and it revolutionized the hard drive industry. The storage density was enhanced by many orders of magnitude by the introduction of this spin valve by IBM in 1998. Professor Parkin won many prizes for this development, but in particular, he won the Millennium Prize. It's a European prize of 1 million euros, and he won this prize in 2014. And it was for this discovery, the discovery of the spin valve. In 1993, I came to DARPA and started a program called the GMR Consortium. And the goal of that program was to try to find applications of GMR that would be important for the Department of Defense. The consortium was actually at that time supported by a program called the Technology Reinvestment Project, which had as its goal dual-use technologies. And in fact, the work that came out, as you'll see, is definitely a dual-use technology. In 1995, after that program, so that was a 2-year program, it became clear that the development of a non-volatile radiation-hard magnetic random access memory would be very important, particularly for the DoD systems, where this type of memory, radiation-hard, non-volatile, very environmentally robust, was necessary for our space and strategic assets. Okay, so the image in the middle of that slide is the memory that was used on our space and strategic assets in 1995. It's a plated wire memory. It weighs 40 pounds. It cost $250,000, and it had a memory capacity of 128 kilobytes. Now, I took that memory, a memory just like it from, I was also working at NRL at the time. I took a memory looked just like that, brought it to DARPA, and plopped it on Gary Denman's desk and said, I am going to replace this memory with a chip. And you see, ultimately it took 10 years, but we replaced that memory with a chip. That memory you see on the slide was built by Honeywell in Clearwater, Florida, and that they no longer make that memory, but they do make the chip. Now, now in this program, the major contractors were Motorola, IBM, Honeywell, and NVE. And on the next slide, you'll see the result of that program. So the chip on the very top of that slide is a non-volatile, rad-hard, very robust memory made by Honeywell in concert with Everspin. In fact, it's a joint memory made by both those companies. And it is the chip now that is used on our strategic assets. It has replaced the memory that you saw on the prior slide. The middle chips are now produced by a company, Everspin, and Everspin spun out of a company called Freescale Semiconductor, which in turn spun out of Motorola. So there was a lot of spinning going on, but all of that work was really started by DARPA, and most of it, as you'll hear, was supported by DARPA. Now, one of our distinguished speakers is Dr. Jon Slaughter. He's now a principal research staff member at IBM in Albany, and he was instrumental in developing these memories, actually both the memory in the middle and the memory on top, when he worked at Motorola, then Freescale, and finally at Everspin, and now he's at IBM. The bottom chips represent a host of sensors that are made by one of the companies that was also heavily supported by the DARPA program. It started out being called Non-Volatile Electronics. It's now NVE. It's listed on the NASDAQ exchange. It's made millions of sensors, and the company now is worth $500 million. So it's a major success story of the DARPA program. Now, this wasn't the end of the story. So on the next slide, in 1997, there were two major discoveries that were made. The first one was made by one of our distinguished panelists, Professor David Awschalom, who's now the Lieu Professor and Deputy Director of the Institute for Molecular Engineering at the University of Chicago, and a senior scientist at Argonne National Laboratory. Now, the discovery he made that's described there was made when he was at the University of California, Santa Barbara. And what he discovered was a very novel magnetic state that could be induced by exciting a gallium arsenide semiconductor with circularly polarized light. This long-lived magnetic state could be manipulated with current, moved around, and definitely excited the community. It was a very important discovery. As you can see, the covers of Physics Today and Nature highlighted this very important discovery. The second discovery was made in Japan by a scientist named Hideo Ono, and he discovered that if you added a little bit of manganese to gallium arsenide, it became magnetic. Unfortunately, at only 110 Kelvin, but this magnetic state was very different. It could be manipulated by an electric field. So by changing the carrier concentration, you can change both the moment as well as the Curie temperature. And this really, these two discoveries, were the cause of a new program at DARPA, and this program was called Spins in Semiconductors, or the SPINS program. And this project did make major inroads into using spin for a number of different areas. A host of new programs started for metrology, for quantum information, and the programs that were started on the basis of spins in semiconductors was QUEST, Quasar, and I'm not going to name them all, but you'll hear about one of the programs, Drinks, from our last speaker. So the future is very, very bright for Spintronics because there's something new. There's a new magnetic state that was discovered a few years ago, and this magnetic state is called a skyrmion. Now, I'm not going to tell you too much about skyrmions because we have an expert on skyrmions, Professor Ale Lukaszew, who is our last speaker. She is a DARPA program manager. She's also a professor, and she's the Virginia Microelectronics Consortium Professor of Physics at the College of William and Mary, and she's going to be describing her two new DARPA programs. One is called Tea, and the other is called Drinks. So at this point, let me introduce our next speaker. This is Dr. Jon Slaughter, and he's a staff scientist at IBM in Albany, and he's going to describe some more of the history of the MRAM. John?
Thanks, Stu. Okay, great. I said thanks, Stu, but I have to thank him for like 20-some years of fruitful employment. I went to work for Motorola in '96 at the very beginning of the first DARPA MRAM program. And like Stu just said, we were in Motorola, and then we went with the Freescale spin out from Motorola, and then our group spun out of Freescale to form Everspin. And everybody thought when we spun out, we were calling it Everspin because we were forever spinning out of something. But the spin was supposed to mean the spin of the electron, of course, for those who understood that. Okay, so I'm just going to talk about the MRAM thread through that whole Spintronics theme. And I'll tell you a little bit about MRAM technology, how it works. So there are two main flavors. The first one on the left is toggle MRAM, and that refers to a particular kind of writing scheme where you switch the magnetic state using magnetic fields. And basically, in any flavor of MRAM, you have to have a device that has two stable magnetic states, and those have two different resistances. So you write the data as a magnetic state, and you sense it with resistance. So it's a resistive memory in the read. The toggle technology came right out of that DARPA program. I've got the timeline coming up, but it was commercialized. We had a qualified product shipping in 2006, so exactly 10 years after the start of the first DARPA program. And I think you'll see now we can look back over 20 years of how this worked out. And I think it really worked out pretty much exactly like Stu told us he wanted it to, in the sense that you have these companies that have a commercial motivation to work on this technology. And by combining that sort of commercial incentive and the resources that the companies could bring to it with the needs for defense and so on, and in the end, we would end up with a lot more resources and faster progress doing it that way, and I think that's exactly what happened. Along the way, this spin transfer method of switching was discovered. So in this method, we switch the magnetic state, not with a magnetic field, but by actually pumping a high current density right through the magnetic tunnel junction, which is the key device here. And that allows us to scale to much smaller devices and with less current, but the basic idea is still the same. Store data as magnetic state and read it back as a resistance, high or low resistance. So I'm going to build up a little timeline here. I'm going to try not to spend all my time on it, but just to give you a feel. So this Stu just talked about some of this, but obviously there was MRAM research before 1995 or 1996. It was mostly based on AMR, and then GMR was an up-and-coming thing. But in '96 is when I think the money really hit for the phase 1 MRAM program, and there was Motorola, IBM, and Honeywell that were kind of the big companies that were all, in a sense, competing against each other, but yet through the organization that Stu put in place, they had a lot of contact with each other, so that was kind of fun. And then there was a second phase, and then later on you'll see right there, there was the spin torque switching got a round of funding from DARPA as well. But so now here I tried to overlay on that in red sort of big scientific or technical discoveries that drove this forward. And the first one is the one Stu mentioned. In '95, this demonstration of high tunneling magnetoresistance from a magnetic tunnel junction, 10%. Today, everything that people are working on for MRAM is probably in the 150 to 200+%. So there's been some progress in terms of the size of the MR, but it's still the same basic idea. And so you can see that there's kind of a regular, cadence of big breakthroughs, right? There was that. Then spin transfer torque was predicted in, I think, 96. It was demonstrated in like 2001. And then this giant tunneling magnetoresistance using MGO tunnel barriers, that was a big jump up from the previous numbers, was in, I can't quite read my own chart there, but somewhere in the early 2000s. And then to really help scale this to small devices, we have to go to perpendicular magnetization. And sort of practical, so there are demonstrations that are basic, but then there are sort of practical demonstrations. The real practical demonstration was this one in about 2010 using cobalt iron boron alloys. So then I overlaid on that in blue, these are sort of product demonstrations or significant demonstrations by companies for showing some kind of commercial milestone. And if you kind of try to line those up, and you'll see like first commercial MRAM 4 meg, that was Freescale in 2006. Like I said, that's exactly 10 years after we started that program. And if you look at some of the other things like first commercial STT MRAM, that was our 64 meg at Everspin in about 2012. That kind of is 7 to 10 years after some of the big developments that enabled that. And then first commercial perpendicular spin torque MRAM, the 256 meg from Everspin, that's 2016. Again, there's that kind of cadence of the discoveries, the big breakthroughs that are scientific or technical, leading to a product in sometimes as little as 5 years, but more often closer to 10 years if it's more of a scientific breakthrough. So, there are other developments that are coming along. So I think we have a lot of reason to believe that we're going to continue advancing this based on scientific discoveries and technical breakthroughs. I don't think we're anywhere near the end of the road on ideas and breakthroughs in the pipeline. So a little bit of how this MRAM fits into the rest of the world of memory. So this is a very typical way to look at computer memories, where you have storage at the bottom, like hard disk drives, and then sort of moving up, you have sort of from the bottom up, you have lower density but faster access time or lower latency. So you go to solid state storage, and then DRAM, and then the SRAM and on-chip caches and that sort of thing. So this is a typical way to look at the memory hierarchy. And another way to frame that is in this chart where you look at speed on the y-axis, so shorter and shorter access times toward the top, and the capacity you have available on the x-axis. So hard disk drives are way out in the high capacity but slow range. SRAM is super fast but much lower density. Flash, so that solid state storage, is a huge performance improvement over the hard disk in terms of the latency, but you pay a price in density. And then there's this sort of gap between the flash and the DRAM. So there are a couple things. There are various emerging memories that are angling to fit into that space, and this is kind of my view of where MRAM fits into that space. So it's very different. It's non-volatile, so it looks like flash or a hard disk drive in that sense. The data does not disappear when you turn the power off, but the performance is much closer to DRAM, and yeah, you pay a price in density. And this is part of the game, is scaling it to get that density higher and higher to move to the right in density, but keep that performance up. So this is kind of showing where we are now. And like I said, a lot of the effort is to either move it to the right or even put it right on top of that DRAM, because it's getting more and more difficult to embed DRAM in these advanced technology nodes. So you can imagine using an MRAM optimized as like a level 3 cache in place of embedded DRAM. So obviously a lot of other people, companies, there's been lots of effort worldwide. So this is a kind of snapshot of where I think we are today. So Everspin shipping these toggle parts, recently, this year actually is ramping up production of the 256 perpendicular spin torque. That's fabricated in a foundry, Global Foundries in Singapore, in collaboration with Everspin. And they've announced 1 gig in a 28 nanometer process. That would be the next product. Global, as part of that alliance, has their own thing where they're introducing embedded memories. TSMC introducing embedded memories. Samsung introducing it as an embedded memory. Honeywell, as Stu mentioned, works with Everspin to deliver these aerospace military parts that are, so far, I think, all toggle-based, but there's no reason they can't be spin torque. And then there are all the big list of companies that have advanced programs, and there are various collaborations there that get that technology out of the lab and into commercial applications. All of those companies have collaborations with foundries or other companies. So there's a huge amount of activity, and actually this is a really big year for MRAM with all these foundries announcing that they're going into production at advanced technology nodes, 22 nanometer and 28 nanometer. And if you look at what people are presenting at conferences from these companies now, it's all about scaling to the next node and the next node. They've really moved on in terms of where their work is to 7 and 5, a lot of nanometer nodes. All the work is directed now in terms of research toward those really advanced nodes. So that's all I have. Next speaker is David Awschalom, who's a professor at University of Chicago and one of the pioneers in Spintronics. Stu already mentioned some of that early work that we all remember him breaking through for us. Thanks.
Thanks, John. Oh, thanks very much. And special thanks to DARPA and to Stu for tolerating us over the last decade or two and taking risks, which is something you don't see too much these days, but without which I don't think any of this work would have developed. So what was interesting about our own work in semiconductor spintronics is I think the most impactful part of it was largely accidental. It wasn't planned. So we approached Stu at the time when I moved from IBM actually to Santa Barbara with an idea to build new experimental techniques, essentially femtosecond optical techniques to stroboscopically look at how an electron spin would interact with a magnetic atom to understand the origin of ferromagnetism. It wasn't really clear how this would work, and I don't think we articulated our vision particularly well. Actually, not well at all. I reread the proposal, actually, before coming here, and it was just shameful. Nevertheless, we're very grateful Stu funded it, and that experiment did work, actually, and it produced some very interesting science, but the most exciting part about that project wasn't that effort, but it was the control measurement. It was when all the magnetic atoms were pulled out of the material, and a control study was done in a commercial wafer of gallium arsenide, and that's the data on the left, where, as Stu mentioned, we used an optical technique to create spin-polarized electrons and just wanted to see how long the spin would be preserved in that material. And it was expected to be very, very short, both experimentally and theoretically. And to our surprise, if you look at the second curve in that yellow panel, you'll see a quantum superposition of states moving as a function of time, slowly decaying, but decaying orders of magnitudes more slowly than anyone expected. And it was evidence that you could create and observe very robust quantum states in conventional semiconductors. And on the right, when we applied a small battery to try and push this ensemble of quantum states through gallium arsenide, and these were commercial wafers, they moved 100 microns or so with remarkably little dephasing. So they were robust. So you could make them, you could move them, and in some work with Berkeley a few years later, using some chemically synthesized quantum dots, which you can see the TEM in the bottom, We again, with millions of these dots with one electron in each, we showed even at the level of one electron, but we couldn't see one at the time, you would still have quantum coherent states in semiconductors. So it was a really exciting development. And one of the things I'm very grateful about with DARPA is it not only drove an interesting field, but it inspired a legion of students to think about being as creative as possible in this area. And at the end of the day, when we tried to understand this physics, and it emerged in many materials from gallium nitride to 2,6 semiconductors, the cleaner we would make the material and the more expensive the material, the worse the experiment was. So oddly enough, again, the dirt was actually pretty important. And at the end of the day, what we learned is with the decades of semiconductor technologies pushing defects out of materials, it was the defects you wanted back in the materials to create quantum states. And one example more recently is diamond, another wide bandgap semiconductor, where the defects in that material trap individual electrons. And the same physics that I just showed works, but now easily addressable at the single electron level. So the data you can see in the upper right is one electron spin at room temperature, moving at gigahertz frequencies. Well, actually not moving at all, but its quantum state, those are Rabi oscillations moving between spin up and spin down, a superposition of states, going on for surprisingly long periods of time, actually all the way to 700 Kelvin. From 700 Kelvin down to 1, very robust. And these experiments were actually inspired by early work at the Naval Research Lab, where not so far away from here, people were doing spin resonance measurements at the NRL, using the resonance to look at defects in diamond, also to try and remove them, and understand how you could grow clean materials. So that got us thinking, what could you do? And this was, I think, in the footsteps of exciting work going on in the atomic physics community, superconducting science community, and now solid state, using quantum states as a new way to manipulate information. And I'm sure everyone in the room has heard about quantum computing, but it's important to also bear in mind that also communication and sensing are the other two legs of, I'd say, this growing field. Quantum communication has the interesting option that these quantum states obviously are sensitive to how you measure them, right? When you look at a quantum state, you perturb it. That could be a liability, but it's also an asset for secure communication. You can use it as a means to control the quality of the information you send. So thinking about this, we began to wonder, why did these states work so well in diamond and gallium arsenide? What limits the materials in which one could observe this? And there we undertook a year-long theoretical effort with a group at Santa Barbara, applying density functional theory as a type of genetic screening. What materials were around where you could build quantum systems? And what came out of that was pretty surprising, dozens of materials. And this is an example of one, silicon carbide, a very common industrial semiconductor for high power electronics, right, and solid state lighting. Those of you with a Prius are using it all the time. Those of you that took an Airbus or a Boeing craft, you probably used it. And sure enough, based on the theory predictions, that data you're seeing is one electron spin in a 4-inch commercial wafer of silicon carbide, beautiful quantum state control with 99% fidelity, running at about 2 gigahertz and emitting light at near telecom wavelengths. And using a common industrial implantation technique, it's obviously easier to add defects than to remove them. So by shooting electrons or ions into apertures, you can make arrays of these, and to think about building wafer-scale quantum systems. Now, we're not there yet. These are just proof-of-concept measurements, but it's a really exciting direction, largely inspired by DARPA and the DoD. Now, I don't know how many physicists are here in the room, but as a physics professor, I'll just assume that all of you are physicists, and take 30 seconds to talk about entanglement. How many of you remember entanglement? That's good enough. That's great. So one of the nice things about these electrons is that near every electron is a nuclear spin. And one of the nice things about having exquisite quantum control of one electron is you can use it to control the single nuclear spin. And this data in the upper right shows some recent developments based on a Muri consortium run by the DoD that you can control independently of the electron single nuclei and have a subatomic quantum memory element that has a relatively long lifetime, and then take that memory element and extract the information back by the electron. So not even close to what Jon has talked about with read and write with magnetic domains. This is a simple read and write quantum one-atom memory that works 80% of the time. So Jon's controlling his laughter, not even close to something useful. But it's, again, a proof of concept that with still relatively naive materials expertise, one can understand the physics of single control and entangle the two quantum mechanically and have pretty robust solid-state 2-qubit systems, an electron spin and the nuclear spin quantum mechanically linked that one can then scale for information processing. So when we think towards the future of the work that DARPA's inspired, we find this really exciting. Now, a lot of people, I think, have seen this, but I do think it's worth emphasizing why this is an interesting area of science. You know, we just heard about memory elements at the megabyte and megabit and gigabit levels, but the interesting thing with quantum systems is even with 50 to 100 qubits or quantum bits, something remarkably small on today's standards, you can still explore some very interesting scientific problems. And these numbers are just to show you that even with 50 entangled quantum states, you would need a classical computer today with 10 to the 15th memory elements just to record all of the states of those 50 qubits. And if you went to 100, you're at 10 to the 30th memory elements. So even with 100 quantum bits, you're beyond the level of today's supercomputers. It's a very exciting direction for the DoD to be pursuing. And since many of these states emit light, you can build encryption channels or entanglement links, which is shown recently by this recent Chinese satellite demonstration, and use these entangled states as a conduit to transmit information over very long length scales. So I want to end with this last slide to say there are a lot of things happening in this field based on spintronics, which naively started with trying to control one electron spin, has now moved into the quantum domain. And already people are thinking of wild applications with quantum sensors for electric fields, magnetic fields, thermal fields, in biological systems like that HeLa cell shown in the middle, to work done with IBM a few years ago in the upper right, trying to use these quantum states to push MRI to the level of single molecules. That alone, if it can be done in the next decade, we would argue would revolutionize areas of biology and chemistry, independently of information science. So with that, I think I should stop and introduce our next speaker, who I think needs no introduction for all of you, the program manager at DSO for this area, and who's our future. Ale.
Thank you. Thank you so much, David. Oh, sorry about that. So yes, I'm Ale Lukaszew. I'm the current program manager that is trying to tackle where Spintronics left off, particularly based on some of the most recent discoveries that have been happening in this particular field that pertain to topology. And I will be trying to explain a little bit to you what is that we have been seeing and why is it that this could be an interesting venue for new developments around Spintronics. So one of the things that is motivating this research is that basically the current technology that we have that was described earlier is reaching fundamental limits. That is, this is a plot that is showing you the reduction in bit size in a standard type of storage device, either solid state or hard drive, and how this is reaching limitations given by materials as we have them right now, because below a certain size, they become significantly unstable. So the question is there anything we can do in order to achieve stability while further reducing bit size? And that is one of the things that these new programs are trying to find out. So this happens for the following reason. In the present technology that utilizes magnetic materials, what we have is a configuration in which the spins of the electrons that are in the magnetic atoms are aligned, and we assign a 1 to this particular configuration and a 0 to the opposite configuration, and that is what allowed us to construct everything that we can in terms of binary language. And the reason for this to be is because all the electrons like to be parallel in a given material, a magnetic material, for example, but this is only up to a certain size. If you go below a given size, then there isn't enough strength in numbers, if you wish, to keep the orientation of the spins. And so that makes a particular entity, that bit of information made of parallel spins, unstable. And so if one flips, now the entire organization of the spins can suffer and you lose the information that was stored. So what we have found recently is there is a different way in which when you can actually organize the spins, and this is when you have them canted. That is making an acute angle between them. And this can be actually engineered by playing with interactions that we have now recently been able to observe and manipulate in materials that allow this configuration. But basically, if you think for a minute, how can you actually place these canted spins on a surface, you see that you have to kind of acquire a vortex type of configuration as depicted in the center lobe part of the figure. And basically now, if you want to flip this, because the spins are locked because of this canting mechanism, now in order to flip one, you have to flip the entire unit. And that is what brings stability to this structure. And it has been reported in the literature already that these configurations are possible and are possible at much smaller sizes than what the current technology can achieve with the parallel spins. So another thing that we have seen is that in order to create these structures, which are basically on a given material just trying to force this canting, you can, for example, start for a material that can sustain those structures and inject a spin polarized current that forces this configuration on the spins. Now, once you have this, another thing that can be shown is that you can apply a current to move them around without expending a lot of energy in doing such motion. So this opens up, these discoveries open up a new form of doing memory, for example, because now you can envision, you can engineer these materials, make these very, very small structures that are significantly smaller than the bit size that we have right now, and we can move them around with very little current, and we can make them move very, very fast, which enables all of these capabilities that Jon was talking about earlier in terms of what matters for memory, right? For a memory application, what matters is density, which means the bit size, but also the energy that you need in order to read them, and also how fast this thing can be written on so that the information can be stored very quickly. So this is actually taken from some simulations that were carried out by people in the field. So these discoveries prompted me to actually come up with new programs within DSO that exploit these topologies such that we can investigate what are the limits for this, because now we don't really know. How small can we go? How low is the energy? How fast can we move them? And are there any other applications that we can see? That I will tell you a little bit about that. Another thing that prompted me to look into what has been happening in the recent literature is that we were hearing also about the coherence of some of these entities in order to keep their information. So is there a way to enhance coherence time? And I also was able to implement a program that works on that front, on trying to enhance coherence time. So I will be telling you a little bit about that. Another thing that one can do with topology is to try to accommodate a different type of structure, not just this canted of the spins. It has been postulated that it is possible to generate quasi-particles at edges or interfaces that are amenable to be moved about one another, and in that movement acquiring a different phase. That opens up the possibility of invoking this technology to create qubit, because a qubit has more than a 1 and a 0, has this phase information involved in it. So it is possible then to create quasi-particles that will enable a different type of computing using qubits, which is this circulating one about the other, which enables a complete different paradigm for doing quantum computing, which is the Kitaev logic that has been, or formalism that has been postulated theoretically. And why would that matter? Well, because these type of structures are topologically protected and therefore will require significantly less error correction, and that will buy you what the current technology cannot buy you, which is to have a lot more scalability of the qubits for use for use in the actual computation. So this is another area that this particular program, T, is exploiting. The counting of the spins for denser, faster, low power standard memory, and the possibility of a complete different paradigm for qubit information. So the other program is about trying to enhance coherence time. So what I will be showing you in this particular movie is how is it possible to apply an external drive to enhance the stability of an otherwise metastable situation. So here what I'm showing you is a vertical pendulum that if you have the bob on top will try to go down because that is an unstable position. And in the video you will see that by driving it, this particular situation becomes stable. Can you please run the movie now? So that's the unstable. And now we drive it. So it's still an upside-down pendulum, but the driving mechanism had introduced stability on this particular configuration that was not possible before. So this is very, very exciting, even though it is a classical example, but it has also been postulated to be possible to drive a many-body particle, a many-body spin system, applying this type of idea, this type of principle, such that you enhance the coherence. And following from the example that David brought up and how you can use defects on materials like diamond to actually probe magnetics, and this is one of the things that people are using diamonds for, to do magnetometry. One of the things that we've seen is that this type of technique, using NV centers in diamond as magnetometers, it is very, very good in spatial resolution, but it suffers from sensitivity. Now, if you actually were to use several of these NV structures in a manner that they do not conflict with one another because you're driving them, you should be able to have the same resolution that with substantial increases in sensitivity. So that's another thing that this particular program is trying to exploit. How to enhance coherence time such that you can improve upon what we already have, but further, it is also possible to induce new phases in materials, like, for example, it has been demonstrated in literature that you can light-induce superconductivity. So the question is, can you enhance the lifetime of this new state by driving it in a particular manner, like in the case of the NV centers? And that, if we were able to think really, really ahead in time, could in principle enable those quasi-particles that we can braid for qubits to operate at actually room temperature, because now I can induce superconductivity in the systems with light, for example. So those are the things that these particular programs are trying to exploit. These are new programs. T started at the beginning of this year. Drinks is going to be having its kickoff now in October. So we're still waiting on the performers to demonstrate some of the things that we have asked them to do. We have given metrics that we believe are reasonable, are realizable, and so hopefully at the end of the day, we should be able to offer the community perhaps a new platform for memory, perhaps a new platform for quantum qubits or for quantum sensors, and perhaps even for the current technology like we have, like for example for atomic clocks, new ways of dealing with the interactions such that you can enhance the stability and the reproducibility of the measurements that are carried out. So that's what we have right now. Is there anything else that Spintronics can offer? Well, there are some proposals out there that it may be possible to use Spintronics to generate devices that can mimic the way neurons work. So the next generation of hardware that will be able to perhaps support the next generation of artificial intelligence still needs to be made. So there is a very strong case for perhaps having Spintronics to be able to come up with these devices that will have a performance and additional characteristics that will enable that particular field to grow. And perhaps there are additional sensing modes in operations that we are not aware of that the community may offer us in years to come. So that's where we are. And I'm a current program manager, so if there is anybody here in the audience that has ideas for example, new concepts for hardware for neuromorphic, new concepts for topological excitations, please look me up, try to get a hold of me, send me a white paper so that we can see how feasible this is in order to implement either a disruptioneering effort that is a shorter type of investment in time and financial burden. But in addition to that, we have also our bona fide programs that are longer. So, I mean, I need ideas from the community in order to move forward and to keep pushing on this field. So that's all I have. Thank you.
All right. Let's thank the speakers again one more time. And I think the floor, I think we have a few minutes for questions. Okay, this question is, what do you think are the most important DoD applications of Spintronics? I'll address that to Ale.
Well, you know, I mean, we have been talking about the possibility of having better, denser, faster memory. There are a number of applications in DoD that use, I mean, in everyday operations that use memory. Stuart was mentioning that current technology utilizes memory that has been developed through this program. So faster, denser memory is always a capability that will enhance the performance of the resources that we have right now. So that's basically why we're investing in this. You can also envision that, and one of the things that I'm thinking all the time, if you have, for example, if you think in the soldier carrying all the apparatuses that he or she needs in order to perform duties, they also have to carry a lot of battery on their backs in order to actually supply for this. So if we can offer them devices that can outperform what we have right now for less power requirements, that means less battery on their backs. And so that is definitely an advantage that this particular type of technology can offer.
Here's a question for Jon. Where do you think some of the sensors that are being built can be applied?
Oh, okay. You know, the same kind of technology that's used for MRAM is used in sensors. And of course, the first application for both GMR and TMR commercial application was in readers in hard disk drives. So that's kind of an obvious one, but those have branched out. So, you know, NVE, that started out as more of an MRAM company, their main business now is sensors, and they have a real big business doing all kinds of sensors for isolators, and for instead of an optical isolator, you can do it with sort of spin valve type structures. Everspin, where I used to work, actually people don't realize it because their tagline is the MRAM company. But if you listen to their quarterly conference calls, you'll hear about a lot of revenue coming from sensors. And that's a really beautiful single chip 3-axis sensor. So that's a compass on a chip. And I think don't know the numbers exactly, but I suspect they've shipped more than 100 million of those sensors by now. Yeah, so I mean, those are some of the big ones. There are all kinds of applications, for example, in automotive, where currently they use different kinds of sensors and potentially using TMR devices, these magnetic tunnel junctions. In other words, for the sensing element can give bigger signals, and so the sensor can be farther from the thing it's trying to sense, and so on. So lots of practical applications.
Okay, thank you, Jon. Okay, this question, I think, well, it's maybe Ali and maybe Jon could comment. Do you think a spin memory based on skyrmions can compete with flash memory in the future? You talked about DRAM, but the question is, can it compete with something like flash?
If the metrics are achieved, it should be able to compete because it will have the density, it will have the speed, and it will have the very low power consumption. So it will definitely be a fierce competitor. I mean, all the metrics have to be there, though.
But I think Jon can comment on the challenges that are there to make a new memory. So
yeah, the challenges are immense. But if there's a commercial motive, it'll happen. And obviously, NAND flash has taken over that whole space. And that's because the density can be very high. So the current way that we build MRAM is really challenged to reach that kind of density. I mean, nobody thinks it will with the way that we're doing it now. So there has to be some breakthrough that would let magnetic or magnetoresistive memory play in that space. So that's maybe a candidate breakthrough.
Yeah.
So there are various things in the pipeline, if you like. I like to think of it as sort of a research pipeline that, like I said before, after about 10 years or so of work, maybe it can be in a product. So that's
the program is
density
aiming
issue
at getting bits below 10 nanometers. It's trying to beat the terahertz rate, and it's trying to beat the femtojoule. So it would definitely compete if all these metrics are satisfied, which is not so impossible. I mean, the materials are there. It would be a question of implementing. But I think it is definitely, all these marks will be there. It will be just a question of how easy is this technology to be put forward into a foundry.
Yeah, and the bigger picture is scaling is slowing down, right? I mean, we're kind of post-Moore's law already. And the way that we're continuing to get higher and higher density is by going 3D.
Right.
So you can only take that so far. So, what else have you got?
Oh, but there is the possibility.
Everyone will be looking for, some breakthrough to take us past that.
There is possibilities of going 3D with this because there is the racetrack devices that have been already postulated with domain walls that this particular type of technology may be a little bit better in terms of velocity than those. So
yeah, I'm saying that whatever they're doing in semiconductor now is going more 3D just to keep the progress going. So if we can find something that has fundamental advantages and then go 3D, that'd be awesome.
Okay, this is a question for David. Will electron spin be the ultimate qubit, since it is the prototypical qubit? Okay, put you on the spot.
I think the right answer to that depends on what the application is.
Okay.
I mentioned before there's computing, there's communication, there's sensing. So I would say every qubit is also a sensor, right? There's a question of how it sees the environment. If it's completely isolated, it's great for computing. If it's not so isolated, it's great for sensing. So I might argue for sensing and communication, electron spins will be fantastic qubits. I think they're already proving there are interesting candidates, for example, in silicon for computing. All of these technologies have challenges in scaling. You think MRAM has problems. Scaling to 10,000 to 1 million quantum bits and entangling them is an extraordinary challenge. But to shorten that answer, I think targeted sensing applications for electron spin qubits will be enormous. I think it's a very open field, and they're great candidates.
Okay. Ali, do you want to comment, or?
I think that, no, I mean, there are a number of things that we look into the future as opening, new options. As I said, for example, spins in the case of Majoranas, means spins in the case of sensing NV centers, right? There are a number of things out there that we have not yet found the ultimate limits that there are. This idea about driving and enhancing coherence time for a number of things that we have not done yet. I mean, all of this opens up possibilities, even for things that we already have. I mean, for example, clocks, atomic clocks that can be made smaller But then in order for them to be as good as we would like them to be, perhaps we can drive them so that they are like, better than what we can make right now. And that is already an improvement in the direction of making small swap, which is something that is of interest in defense all the time, right? So that's basically where I see this going.
And I think areas like targeted molecular sensors.
Yes.
So if you want to look at a particular molecule at a very large distance, there's no issue with a quantum sensor seeing one molecule, period. I mean, you can do that today.
Yeah.
So I think engineering those systems into useful DoD applications, those opportunities are extraordinary.
Yeah.
And I think we've just begun to see what you can do with that.
Yeah.
Okay, well, this is similar to another one, but I guess it's for Jon. Will past work building spin-based devices help in the design of skyrmion-based devices? So do you think all the experience that you've had building MRAM will be useful if you're going to find that skyrmions are useful?
Yeah, I mean, I definitely think so. In the end, we need to have arrays of devices, and we need to read and write them, and they need to be made out of something that may look like a magnetic tunnel junction. So I think a lot of that technology would be the base for skyrmion-based electronics.
Well, in a way, magnetic bubbles were considered at some point for memory. And right now, the skyrmion is like a very, very tiny bubble that has this added protection because of the topology, right? So, I mean, it's not that it was not in the realm of possibilities at some point to use this type of thing for memory, so.
Okay. We're running out of questions, but we're not running out of time. But I have one more question. What do you forecast will be the length of time before new technology based on skyrmions is adopted by the DoD? So who has a crystal ball?
Well, I mean, if we were to, I mean, I am now influenced by previous talks about, how long does it take for things to be reproducible, right? So if I were to mimic what happens with Spintronics, how long did it take between the discovery of GMR and an actual device? You witnessed that. How long was it? 10 years?
No, it was 10 years since a really serious effort was mounted to actually build something rather than just have an academic. So there's a big difference. I'll answer part of this question. There's a big difference between academic research, which is very lucky to even be able to demonstrate a program, and an industrial program where you have the discipline necessary to make multiple devices with very good margins. In other words, the devices all have to fall within a very narrow range. And the ability to do that takes a lot of money. And it's amazing. I mean, one thing that Jon didn't say is that when the decision was made to really make a product out of MRAM, and that was made at Motorola, there was a very large investment made in modifying a fab in Chandler to actually do that. It was a multiple, probably over 100 million, maybe more, dollars. That wasn't DARPA dollars. It was company dollars. So at some point, that type of discipline of a true foundry needs to be put into play. And so, I mean, it's very nice to have a lot of academic research demonstrating that a technology can be used in DoD or commercial systems, but then it takes a lot of resources to actually turn those discoveries and those prototypes into something that you can buy or put in your iPhone. So it's very hard to say. Somebody has to bite the bullet.
But that's true. But the way I see it is that there has to be a real need. I mean, once there is the bottom line and the current technology just will not budge, then somebody will have to do something about it. Because, I mean, there is that small you can go. There have been all sorts of tricks that have been played in order to try to make it better. I mean, playing with the magnetic anisotropy, heat-assisted recording, you name it. Every trick was tried to be played in order to improve upon what we had. Eventually run out of tricks. And so you need new technology. And so.
Right. But again, even to make the memory, it requires
Money.
A large investment. And it's typically not money that the government provides, unless the need for the DoD is so crucial that they're willing to pay the whole price. I mean, the DoD pays for a submarine. It pays all of it. but it didn't really pay for all of memory or computer chips. The commercial investment outweighed the DoD investment, even though DoD may have seeded it. At some point, the companies made the decision that this was going to make a lot of money. And anyway, I think we have a few minutes left. I'll be willing to entertain a question from the floor, if anybody has a question. Yes, in the back.
Yeah, it's a very naive question, but can you give us your sense of the current state of quantum computing outside of a laboratory setting? Because there are many reports of its commercialization that are then sort of subsequently dismissed. And I'm just wondering what that status is, or whether it's just black and therefore sort of invisible.
Well,
David?
This is being recorded, right?
It is being recorded, but it's not going anywhere. It's not going to be released to Congress.
Yeah, maybe a nice way to answer that is, 4 or 5 years ago, there wasn't a lot of industrial interest. Today, I would say virtually every major technology company has a quantum technology program. Google, IBM, Microsoft, Intel, you can go on.
Ball. Believe it or not, they are interested.
Okay.
All industries.
Yes, but we're being recorded. Yeah. So, no, it's a very good point, and the numbers are growing. The number of startups is growing, actually. So, I'm not sure how to answer that. I mean, there are lots of different approaches. I would say by far the leading contender for a scalable system now is using superconducting qubits, which makes sense. Superconductors have built-in coherence. And those devices have been engineered for, 40 years and more. It's really become an engineering issue right now and a material science issue, which is terrific. So you're right. You do hear stories in the news of there already are dozens of qubit systems running. There's an expectation there'll be a 70-odd qubit system announced this year. You saw from my chart briefly, if you remember that 70 qubits is a very interesting point because it will allow you to run certain applications that are beyond the scope of today's computing. It'll be a great crossing point scientifically. But it's a tough technological challenge right now, and just the scaling issue.
And if I might just sort of follow on, and what about quantum communication? I mean, it seems that sort of the entanglement and separation seems naively more feasible.
That's correct. No, you're absolutely right. It's an easier problem to address with quantum communication. You don't need the massive level of entanglement and high fidelity that you absolutely have to have with computing, which is why, for example, the Chinese program with the satellite is so interesting, because they're already over transcontinental distances having strong entanglement and teleporting. They're about to announce the Beijing-Shanghai link, right, which is a fiber link between the two cities for doing encryption and communication. So this is really happening, and I think, if nothing else, like Stu was saying, one of the big drivers is also the finance sector that would love to see even short-range networks running. So I very much believe we're going to see that in the next few years.
Yeah.
Yeah, but one thing I want to point out is that there are two types of qubits. There are physical qubits and logical qubits. And so far, at least I think the computers that have been built, these 50, are still physical qubits. And they can play a role. There are some problems that you can do with physical qubits because you can check, even though you don't know the answer, you can check the answer. But to do other problems, you really need logical qubits, which means you've done the error correction. Just as was said, you need 99.99999 in terms of fidelity. And for that, you need logical qubits, and I don't think we're there yet, but we may get there.
Well, the error correction is the big hurdle.
Right.
It has to be, it's a huge drag on the systems right now. But the excitement is the opportunity space. So a few years ago, this recent demonstration with 3 qubits of solving the entire set of states of the hydrogen molecule, for example, all the states with 3 bits. It's remarkable. That's still a pretty sophisticated calculation to do on a large classical machine today. So I'm very optimistic this will happen. But it does need industry, like Stu was saying.
Okay, so we're out of questions, we're out of time. Let's thank everybody again. I thank the audience for coming and listening, and enjoy the rest of the meeting.